Hello and welcome to this lesson on amino acids and proteins. Our learning objectives for this video lesson are: firstly, we want to realize that amino acids have both acidic and basic properties. Even though they're called amino acids, they do have basic properties under certain circumstances. We want to be able to name amino acids, lots of different types of amino acids, and from their structure we'll work out their name, or vice versa. And we're going to come across a concept called zwitterions. Zwitter is the German for hybrid, so hybrid ions. And then we're going to have a look at how you would separate amino acids by means of chromatography. And then we'll move on to proteins, proteins being sequences of amino acids joined by peptide links, rather like condensation polymerization. And the reverse of the polymerization process is hydrolysis. And if you hydrolyze the peptide link, you get back to your constituent amino acids. And then lastly, we're going to have a look at hydrogen bonding. Not just in water, also in proteins. And why is it important? Okay. So first of all, before we get into the details, we're going to just study what an amino acid is. And the fundamental thing about an amino acid is it has two functional groups. It has an amino group, hence amino, and it has a carboxyl group, hence acid. So we're going to draw a typical amino acid, and we usually start with the central carbon. An amino acid usually has a central carbon and an alkyl group, or that could be aromatic as well, and it has a hydrogen, and off either side it has its two functional groups. So off one side it has the amino group, like so, and off the other side of the central carbon atom it has its carboxyl group, which you'll be familiar with. Okay, so we're just going to name those. This group here is our carboxyl group. This group here is our amino group. Let's just annotate these two as well. We've got a variable alkyl group. So what the alkyl group is determines what acid it is. We have a hydrogen atom here, and it's worth pointing out that we have a central carbon atom. Like so. So that's what an amino acid looks like, and the variation usually comes in what alkyl group we have. So that's the first important thing about amino acids. And the next thing that we're going to look at is a function of the fact that an amino acid has these two functional groups. And that is that an amino acid is amphoteric. Amphoteric means that it can act as an acid or a base. And here's how. The carboxyl group allows it to act as an acid. So let's draw the carboxyl group. So that can dissociate, that carboxyl group can dissociate, and it's not a one-way reaction, so we use the equilibrium sign. It can dissociate into the hydrogen ion and the conjugate base. So what you can see is that the carboxyl group has donated a proton. In this process here, and that by definition makes it acidic. And of course it can act as a base as well. So when it acts as a base, it is the other functional group that acts as a base. The amino group that is attached to the central carbon atom accepts a proton or a hydrogen ion. And in the same way, that's an equilibrium reaction. So the functional group becomes an H3+, and so you can now say the amino group has accepted a proton. It's accepted a proton, and so by definition, the Bronsted-Lowry definition of a base, that makes it a base. And so you can see that the one amino acid can act either as an acid or as a base, and the word to describe that property is amphoteric. But one other feature before we move on to naming amino acids is to do with their symmetry. And so we can say that amino acids are chiral molecules. And let's just make sure that we understand what chiral means. You may remember that that is the left-handedness or the right-handedness of a molecule. So the molecule might exist in two forms. It's the same molecule, so it has the same structural formula, but one version of it is the left-handed version and one version of it is the right-handed version of it. And that means that they are mirror images of each other, but they are not structured identically. So we'll show you with an example. So this is an L-amino acid, whereby we've got our central carbon atom, and we've got our amino group on the left and our carboxyl group on the right. And then we have the same amino acid, but this is called the D-amino acid. So you can see the carboxyl group is on the left this time, and the amino group is on the right. So they would have the same formula, but the same molecular formula, but their molecular structure is different. If you were to draw a mirror down the middle of them, you can see they're mirror images of each other, but you can't superimpose one on top of the other. And you might remember chirality from your biology GCSE when you studied thalidomide. So what we can say about chirality is these two amino acids, the L-amino acid and the D-amino acid, they are enantiomers of each other. Now, in nature, most amino acids are in the L form, as it happens. You get the odd one that's in the D form, but most of them are in the L form. So that's the other feature of amino acids, as well as their amphotericness. So now we can go on to naming amino acids. And thankfully, the naming of amino acids is systematic, which means we can learn it easier. And here is the systematic process that we go through. Number one being we name the longest carbon chain that includes the carboxylic acid. And then we take the carbon in the carboxylic acid and we number that on number one. And then number three is we would write down the positions of the amino groups. And number four, we would name and number the other functional groups. So that, as it stands, doesn't make much sense. So let's go through a few examples and make sense of that. So here we've got an amino acid. This is our simplest amino acid, where the alkyl group is just another hydrogen, you see, coming off the central carbon atom. So before we even start, let's just remember that the systematic names for all amino acids end in oic acid. So we're going to write the end of the name first. So it's going to be something oic acid. And that's always the same in the systematic name. So then we go to step number one, and we name the longest carbon chain. So here we've got the carbon chain here, including the carbon in the carboxylic acid. And so we can remember that 2 carbons gives us ethane. So this is going to be ethanoic acid. So let's just write the ethane like that. I've put it in a different color just to illustrate the different step. So this was the green step. So let's just number our carbons. This will be number 1 and this will be number 2. And so now we have to write down the positions of the amino groups. So the amino group here, you'll see, is attached to carbon number 2. So we call it 2-amino ethanoic acid. Two-amino ethanoic acid, and that's the name of this particular amino acid. And if you were interested, it has a common name as well, of glycine. Okay, so let's do another example. Let's slightly build up in complexity. So again, let's write down our oic acid before we even start. And then I'll switch to green. And so now we can name the longest carbon chain that includes the carboxylic acid. Okay, so this is the longest carbon chain here. And that's got 4 carbons in it. So that's going to be butanoic acid. Butanoic acid. And now we'll number the carbons. Switching to red. So again, we start with the carbon in the carboxylic acid. 2, 3, 4. And so now we're going to write down, so we're going to have 2 amino, see, because our amino group is attached to, we're going to have 2 amino, and we've also got a methyl group here, which is attached to the 3rd carbon. So we're going to have 3 methyl. So in which order do we write these in the name? Do we write the 2 amino first or the 3 methyl first? Well, as it happens, this is just something you need to remember. We write 2 amino, 3 methyl. So let's write that down. And that's how we write that middle amino acid. And in case you're interested, that's common name is valine. I'm just going to draw a little black line here because I don't want it to get it confused with the 3rd one that we'll do, which is here. So as we did before, let's put our oic acid down. There's our oic acid, and then we'll switch to green and look at the main carbon chain, which is there, starting off with our carbon that's in the carboxyl group. And so you can see 3 carbons in the main chain. So that is going to be prop. So it's going to be propanoic acid. Propanoic acid, and then we need to name the other groups, the amino group and any other functional groups that we've got. And you see in this one we've got, as well as an amino group, we also have a phenyl group here. And the amino group is attached to carbon number 2, and the phenyl group is attached to carbon number 3. So we're going to write down 2 amino, 3 phenyl. 2 amino, 3 phenyl propanoic acid. And that common name is phenylalanine. You don't have to remember these common names, but you do have to be able to work out the name of an amino acid from its structure, or in fact go in the reverse direction and draw them from the name. So let's just check our learning objectives, see where we've got to, and we can safely say that we've done the amphoteric nature of amino acids, and we've just worked out how to name amino acids. So now we're going to move on to the concept of zwitterions. You might remember I said that Zwitter is the German word for hybrid. So here we have a statement that says a Zwitter-ion is a dipolar ion. So let's just make sure we understand that word dipolar. So di, as you know, would mean 2, and polar, think of charges in this case, as in electric charges. So it's going to be an ion that has 2 charges on it. So as we've said in the suffix here, we've got a positive and a negative charge in different parts of the molecule. So let's draw one to illustrate it. So we start off with our central carbon atom again, and let's have our alkyl group at the top and our hydrogen at the bottom, and then we're going to have our carboxyl group that has lost its proton. Okay, so you can see this is now an ion because it's lost its proton. It retains the negative charge. So the carboxyl group has been deprotonated. Deprotonated might be a new word, it just means it's lost its proton, because you remember that would normally be an OH group there. And on the other side we would have our amino group, but our amino group could possibly have been protonated. So instead of having the normal 2 hydrogens, it's got 3 hydrogens because the proton has come and attached to the electronegative nitrogen, and the positive charge settles around the nitrogen. So you can see on the left hand side we've got the positive charge, and on the right hand side we've got the negative charge. Negative charge coming from the fact that the carboxyl group, or the OH group, the hydroxide group, has been deprotonated, whereas the amino group has been protonated. So it's accepted a proton, which came with a positive charge. So now we've gone from a molecule that was an amino acid to a dipolar ion. It's got both a negative and a positive charge, and that dipolar ion is called a zwitterion. So here's another interesting concept about zwitterions, and that is that they exist at the amino acid's isoelectric point. So let's just define that for us. So isoelectric point is the pH at which the amino acid is both protonated and deprotonated. And the pH, each amino acid's isoelectric pH is different, because it depends on the alkyl group, whether it's how electronegative the alkyl group is. So let's quickly draw our zwitterion that we had on the previous slide. Our central carbon atom, our alkyl group and our hydrogen, and we have a carboxyl group minus a hydrogen, minus the hydrogen, so it's been deprotonated, and our amino group with an extra proton attached to it, like that. So that zwitterion exists at the isoelectric point. So let's put down isoelectric point here. So that's, I'll put in brackets a certain pH. And at pH is lower, than the isoelectric point, this amino acid will exist differently. So let's draw it in a different color. So we've got the same basic structure. But at a low pH, that is acidic conditions, then the carboxyl group is not going to be deprotonated, right? So you're going to have a hydroxide group, you're going to have a full carboxyl group there. But our amino group is going to be protonated, because there's lots of protons swimming around in a low pH situation. So that's what our ion is going to look like in the low pH scenario. So the corollary of that would be a high pH scenario, in which case we are going to have a dearth of hydrogen ions, and we might have hydroxide ions instead swimming around, looking to soak up any spare protons, in which case our zwitterion would not be dipolar, it would instead be deprotonated. Right, so the proton that was on the carboxyl group is going to be sucked off and by a floating hydroxide ion and made into a water molecule, and there will be no spare hydrogen ions around to protonate our amino group, so it would stay like that. So that's what our zwitterion or amino acid would look like in a high pH scenario. Very quickly then, let's check off our third learning objective, and so we can now see that we're going to move on to separating amino acids by means of chromatography. So I just said that we would separate amino acids that are in a mixture using paper chromatography, but we could also identify them as well, because once we've separated them, to identify them you just need to compare the chromatograms against known, that is chromatograms of known amino acids. So let's quickly go through the process of paper chromatography. You're going to start with a piece of chromatography paper, nice big rectangular strip like that, and then you're going to get your pencil and you're going to draw your line, your pencil line on the bottom, and you're going to take your sample of your amino acid mixtures. Let's make that in green, shall we? So you're going to put your sample down here, and then you're going to use an appropriate solvent in a beaker. So you're going to have your beaker here, and you're going to have your solvent like that, and eventually the solvent will rise up the paper, and it will become the solvent front after a particular time, after a particular amount of time. So this would be your solvent front. We've got our actual solvent. This was our chromatography paper. And our point of origin. And then, of course, the solvent carries up the amino acids. So it's some amino acids are pretty sticky, and they stick to the paper, and they travel up the paper slowly. And other amino acids are less sticky. They have less friction with the paper, and so the solvent carries them up more quickly. And so in a given time, each of the amino acids is going to have traveled up the paper a different distance. Alright, so let's say that's one amino acid, and let's say this was another of the amino acids, and one amino acid got right up there. And each of these corresponds to a different amino acid. So a couple other interesting points would be that amino acids aren't in fact coloured, and so to see them on the paper you have to spray with ninhydrin. Solution. Just a solution that enables you to see the amino acids. And the second thing, in terms of identifying the amino acid, what you would do is, what colour shall I use here? Let's use red. You would measure the distance moved by the amino acid, let's call that A, and you would compare that to the distance moved by the solvent, let's call that B. And so an amino acid, let's say I don't know, glycine, has a ratio A to B in a particular solvent, particularly with a particular paper of let's say 1/3. All right, that might be standard glycine. So if your A over B measures 1/3, you know that the green dot is glycine. So there you go. That's how you identify your amino acids. So very quickly, let's see what we are to do next. We have done amphoteric, we've done naming, we've done zwitterions, we've done identifying and separating them with chromatography. Now we move on to proteins. So we're going to have a look at proteins and how we make proteins up from amino acids. And so proteins are formed using a process called condensation polymerization. You might, in other parts of chemistry, done addition polymerization. You certainly do addition polymerization in GCSE. So this is condensation polymerization, which means we're going to get a water molecule dropping out of two monomers. The monomers being the amino acids. Okay, and the link that links the two amino acids, the two monomers, is called a peptide link. So let's have a look. Let's actually draw one up. So let's, in blue, we'll draw amino acid number 1. So amino acid number 1 with alkyl group R, carbon, hydrogen, amino group, carboxyl group. Okay, and let's draw in green amino acid 2. And so this time we're going to have our dash joined to our central carbon. The rest we can make the same. And what happens is that we get a reaction here where the hydroxide group fancies the look of this hydrogen on the other amino group and takes it and forms a water molecule. So we draw the water molecule over here because it's a product. So it becomes a water molecule like that, becomes a product, and our other product, let's draw that in, well, let's draw that in both blue and green. So we've got a reaction here, and it's an equilibrium reaction as well. We'll come back to that in a second. And so our amino group of our amino acid 1 is the same. This should all be in blue. So this is unaffected with our original alkyl group and our original hydrogen, but our carboxyl group is changed and it slightly reorientates itself. Like this. That's our other alkyl group that defines the amino acid number 2, and our other carboxyl group is unchanged so far. Okay, so this what we have here. Let's switch colour. Let's have a bit of purple. All right, so what we've got here is called a peptide link. Sorry about the writing. So that's the peptide link, that bond between the carbon and the nitrogen. The carbon from the carboxyl group of amino acid 1 and the amino group, the nitrogen from the amino group of amino acid 2. That's a new bond, and we've had our water drop out in that process, and that's a peptide link. And so what you have here is a dipeptide. You have a dipeptide. It's not yet a protein yet, because a protein is a polymer, and this is just like a dimer. So what you would have to do to get your protein is to repeat this many times until you get a big long chain, and when you've got a big long chain, that would be a protein. So I think the last thing just to say here is that the forward reaction here is the condensation reaction. So that's condensation reaction. So you're taking two molecules, reacting them, and a water molecule is dropping out, just like a raindrop is dropping out of the cloud. So that's called a condensation reaction, and that's reversible. What instead you could do is you could take this dipeptide and force a water molecule into it, and that would be called hydrolysis. And if you hydrolyzed a dipeptide, you would end up with your original amino acids. So what we just did is we made a peptide link out of two different amino acids to make a dipeptide. But if we start with two different amino acids, we could end up with two different dipeptides. For example, in the first case we used the carboxyl group of amino acid 1 and we used the amino group of amino acid 2. But we could do it the other way around, and let's just illustrate that with some diagrams. So here's the statement. We're saying that if the two amino acids that are combining are different, two different dipeptides are formed. So in the first case, let's say we've got two different amino acids. This one here is alanine. I'll use the common names. This one here is alanine, just for speed purposes, and this is glycine. Okay, and you see in this peptide link that's shaded out here, we're using the hydroxide from the carboxyl group of alanine, and we're using the hydrogen from the amino group of glycine, and they form this peptide link here, and we've got a dipeptide that's illustrated here on the right hand side. Okay, but we could do that reaction the other way around, as is illustrated here. So we've got glycine has switched over here, and alanine is this amino acid here. We've got the same condensation polymerization reaction happening, but this time the hydroxide group that is involved in the peptide link is from the carboxyl group of glycine, and the hydrogen that is involved in that peptide link is from the amino group of the alanine. And so even though the two amino acids are the same in both cases, we get two different amino acids, number 1 and number 2. And you can see, just look at them and see that they're different. This is different to this, and this is different to this, for example. Okay, that's most of what we need to know about proteins, but I have seen an exam question that asks how you would hydrolyze a protein. So necessarily it's pretty difficult to hydrolyze a protein, otherwise, you know, we who are made out of proteins would hydrolyze when we walked out in the rain or had a bath or a shower. So that wouldn't be good. So it's pretty tricky to hydrolyze a protein. So what you need to do is you need three things. First thing is you need some 6 molar, i.e. pretty concentrated hydrochloric acid, and you need to heat that under reflux. So that's again pretty harsh conditions. You need to heat it under reflux, i.e. boil and condense it, you remember. And you need to do all that for 24 hours before you can hydrolyze a protein. So I have seen an exam question that asks you what are the conditions under which you would hydrolyze this protein, and it was a 3-mark question, and those would be the 3 marks that you would, 3 points that you would need to give to get your 3 marks. So what we are going to do now is we're going to move on to hydrogen bonding, because we have covered all the way down here, as we've checked previously, and we've also just done hydrolysis of the peptide link as well. So hydrogen bonding, let's say a very quick reminder of hydrogen bonding. Let's say we've got some water molecules here, and oxygen is so electronegative that it's going to draw the electrons from the 2 covalent bonds towards itself and give itself a negative charge, and that's going to result in also a positive charge on the hydrogens. So water is a polar molecule looking like that, and so when the negative oxygen is adjacent to a positive hydrogen, you're going to get a hydrogen bond there, which is stronger than a van der Waals intermolecular force, and it's a reasonably strong bond. And so it's quite influential in proteins, because we get a lot of hydrogen bonding in protein, And what we're going to move on to now is to find out why that hydrogen bonding is important in proteins. So, hydrogen bonding in proteins. Let's understand first of all hydrogen bonding before we go on to how that affects the shape and therefore the function of a protein. So what I'm going to draw is I'm going to draw strands of a protein molecule, and I'm going to hone in on the peptide link bit. Right, so we've got a strand of a protein molecule, doesn't matter what that bit is, and we've got carbon and nitrogen. So this is the peptide link, so we've got the oxygen that was in the carboxyl group, and we've got that part of that molecule there. And so a different strand of perhaps the same molecule. Let's draw it in a different color to highlight it. So we've got an amino part and double bond oxygen. So you can see that they are parts of protein chains, like maybe the same big long protein. And what's important is the polarity of these different elements here. So on the oxygen we have lone pairs of electrons, which are very negative. So we just draw those lone pairs in there. So lone pairs are always very dense areas of negative electric charge. And what's more, you've got oxygen as a very electronegative element, more electronegative than carbon, so it draws the electrons in the double bond towards itself, so that that's quite a negative area around that oxygen there. Nitrogen is also quite electronegative, and so the nitrogen draws electrons towards itself. The electrons that it's sharing with the hydrogens in those covalent bonds are drawn towards the nitrogens, which leaves the hydrogen short of electrons, which gives it a small positive charge, like that. And so what you could see is that just in the same way as we looked at with water, you could see a hydrogen bond existing between the negative charge on the oxygen and the positive charge that's on the hydrogen. So that would exist there and also there. And so if this then I'm going to zoom out into the whole polymer, and let's say the polymer was a long chain that looked something like this, and you had this carbon double bond oxygen here, and this nitrogen hydrogen here, and you could have then your charges and your hydrogen bond there, like that, which would keep that kink in that molecule, just like that. And you could have the same existing here. You could have your carbon oxygen, your nitrogen hydrogen, and your hydrogen bond here, like that. And so you can see this shape that I've drawn, as it happens, I've drawn it just like a wavy shape, is held in place by those hydrogen bonds that I've drawn. And that's what is important about hydrogen bonding, because the shape of the polymer determines its function. There, I've written that out for you just because that's so important. So if you imagine an enzyme, e.g. an enzyme, so the enzyme works, you'll remember that enzymes break down large food molecules into smaller food molecules. Enzymes are proteins, and they work by being a certain shape. And it's their shape that allows them to break down large molecules into small molecules. And so if their shape is determined by hydrogen bonding, as it is here in my simple sketch, you can see that that is important to the protein. And the corollary of that is that if you used heat or in fact pH, will often destroy the hydrogen bonding. So the heat or the pH will often destroy the hydrogen bonding and therefore destroy the functionality of the protein, because the functionality of the protein, of course, depends on its shape. So in cooking, for example, you might have heard the term denaturing of proteins. So if you've got some proteins that have been heated very aggressively, then what's happening is the hydrogen bonds being affected, and that affects the shape. If you make these hydrogen bonds disappear, then the wavy shape is going to change. Perhaps it will straighten out, and therefore the protein won't do what it was designed to do. And therefore you see how hydrogen bonding is important to the function of a protein. And that brings us to the end of this video lesson. I hope you've enjoyed it, because we've already checked that we've done these, and now we've also done the importance of hydrogen bonding. And so that's it, and I'll see you in class.